Hello and welcome. Today we're going to talk about solving systems of equations using elimination. So a system of equations is when you have multiple equations lined up, and both of these equations have to hold true for the system. Now, to solve a system of equation means to find a proper x and y value such that it is true for both the first equation and the second equation. A very simple method for doing so is called elimination. This is going to do what it sounds like. We're going to get rid of a variable. So what I like to do is look at my variables, x and y, and ideally they're lined up. Later on, we'll see what to do when they're not lined up. But ideally they are, and they are in this case. And my goal is always just to add them. If I can just add these two equations together and have something disappear, I'm very happy. And in this case, we can't, so let's do so. I'm going to draw a line right under here, and I'm just going to do an addition sign. When I do so, x and x adds to give me 2x. Y and negative y add to 0. Y minus y is 0, so I'm not even going to write anything. And then on the right side, I have it equal to 10 plus 2, which is 12. Now I could solve for x like I'm used to by dividing by 2, because it's the opposite of multiplication, over 2, over 2. And I get that x is equal to 6. Now, this is good. However, earlier I stated that solving a system means to find the x and y values that are true for both of them. So how am I going to find a y value? I only have an x value. I'm going to take this x value and plug it into either of the original equations. It does not matter which, either of them. I'm going to plug it into this one here because it seems fairly simple. And what I get is the following. I get, instead of x, I'm going to put parentheses and a 6 because x is 6. And then I still write the rest, plus y equals 10. Now I have to isolate y. Well, it's a 6 plus y, so I'll minus a 6, minus a 6. Y is now equal to 4. And that's my second part of the solution. So the way I would write my final answer is the coordinate 6, 4. This is an x, y value. And if I want to check real quick that this actually works, I can look back at the original two equations and think, does 6 and 4 work? Well, if I put a 6 plus a 4, that does equal 10. If I put a 6 minus a 4, that does equal 2. And so I'm good to go. You don't have to always do that, but if you're feeling uncertain, you just plug back into the original 2 and make sure that it gives you a valid equation. Let's try another. Here we have the system 3x plus 2y equaling 16 and 3x minus 2y equaling 4. Once again, I have it lined up nicely with x's over x's and y's over y's, constant over constant. And this time I do have numbers next to my variables, but that's okay because this 2y and this negative 2y is lined up nicely to cancel out. So all I'm going to do is add these two together. I'm going to get 3x plus 3x, which is 6x. 2y minus 2y gives me 0, so nothing's there. I write my equal sign. On the right side, I have 16 plus 4, which ends up being 20. Now, in this case, I'm going to have to get x alone again. I'm going to divide by 6 on both sides, over 6, over 6. I get the x is equal to 20 over 6, which is the same as 10 over 3, just taking a 2 from the top and a 2 from the bottom. Unfortunately, this is not a nice even number, but that's okay. It's a fraction, and we can just leave it as a fraction. If your teacher likes decimals, make it in a decimal, but fractions are actually pretty nice, and you just leave it as is. Now, I'm not done. When solving a system of equations, you're not done until you have both solutions. So far, I have 10 over 3, but I don't know what my y value is, so I'm going to have to figure that out. In order to do so, I'm going to take that 10 over 3 and plug it in. Which one would it be easier to plug into? It really doesn't matter here, but I'm going to avoid negatives, so I'm going to go for the first one. So when I plug it in, I still write the 3. I put a parentheses, and then I replace my x with the 10 over 3. I'm replacing this x variable here. And then I write the rest exactly as was. Plus 2y is equal to 16. Now I'm going to solve for my variable, my remaining y variable here. Now, first off, I can do 3 times 10 over 3. That's pretty nice. It cancels. 3 and 3 cancel, give you just 10 plus 2y equals 16. Next, I'm working from the outside in. I'm going to get rid of that 10 by doing the opposite, minus 10, minus 10. I have 2y is equal to 6. And then I'm going to divide by 2 on both sides because that's the opposite of multiplying by 2. Y is now equal to 3. And so my second part of the solution is 3. And this would be my answer. You can double check up here, but you don't always have to. Only if you're feeling not very confident or uncertain would you plug it back and double check, because this is a good final answer. Let's look at another. This time we have y plus 2x equals 10. and 3x minus y equaling 5. Now this is a little different from previous ones because the x's and y's are not properly lined up. The y is not on top of the y, and the x is not on top of the x. So what am I going to do? Well, pretty simple. I'm going to rearrange. I'm going to move the top one around to get the following. 2x plus y equaling 10. And the second one, I'm not going to change. 3x minus y equals 5. Now, I didn't really change anything with the top. I just rearranged, which I'm allowed to do. You can move items that are being added together back and forth. Now that they're lined up nicely, I look and see, oh, y and y are lined up really nicely to cancel each other out. If I were to add this together, I would have a variable go away. So I'm going to do exactly that. So I'm going to add these two equations, and I get 5x equaling 15. 2x and 3x gives you 5x. 10 and 5 gives you 15. That will lead me to say x is equal to, if I divide by 5 on both sides, a 3, which is fantastic. But that's not our final answer. We need to take that 3 and plug it into an original equation in order to find the y value. I'm going to do that for the first original equation. And I always recommend going back to the start. You could try either of these as well, but I do strongly recommend going to the original ones to make your life easier. Now, when we do it, we get the following. Y stays the same. Plus stays the same. There's still a 2, but instead of x, I'm going to put parentheses 3, and it's equal to 10. Now I solve for y. This is y plus 6 is equal to 10. Get rid of the 6. Y is equal to minus 6 on both sides, positive 4. So my solution is going to be the coordinate 3, 4. X is 3, y is 4. Let's try another. In this case, it is lined up nicely. We have x on top of x, y on top of y, 5 and 15. However, there is nothing that would go away if I would add these two together. 3 and 8 would give you 11. Y and y would give you 2y. So what am I going to do? Well, I'm going to need to bring in a negative somehow. One of these has to be negated. I don't like thinking of it as subtracting. I like to consistently always add. So I'm going to begin by putting a -1 and multiplying on everything on the top equation. I did this to the top equation because I want the smaller x to have a negative. I don't want a big negative. The result is this. -3x minus y is equal to -5. Again, everything gets a negative in the first one. The second one I do not touch. 8x plus y is equal to 15. Now, nice and convenient, this y and this -y are going to cancel out. And so I can just add up nice and easy. So 8 plus -3x give me a positive 5x, which is nice. That's why I did the negative on the smaller number. Y's and y's cancel, and I get on the right side a 15 minus 5, which is a positive 10. This will give me that x is equal to a positive 2. And now in order to find the second part of my solution, I'm going to plug back into one of the originals. I'll do it into the second one. Why not? So I have an 8. I put parentheses for 2 because I'm replacing this x right here. That has to be replaced. And everything is the same. Plus y equals 15. 8 times 2 is 16. Plus y is still equal to 15. Minus 16 from both sides. 15 minus 16 gives me a -1. And so my final solution is the coordinate 2, -1. And so when I have a lineup of two positives, I don't have any variables that can just easily cancel. I just multiply by a negative and make things go away anyways. Let's look at another. In this case, x's and y's are lined up, which is nice. They are both positive, so I know I'm going to have to do some negative stuff as well. But what's also interesting is I don't have any lineup in terms of numbers. So if I were to make the top negative somehow, 3x minus x would not go away. 2y minus y would not go away. No variables would disappear. So what I need to do is to choose something to multiply by that both makes it negative and makes one of these variables go away. I'm going to choose to line up these x's. You could do either x's or y's, but x's look nice and easy to me. And the way I'm going to do it is I'm going to multiply a -3 on the top, -3. This gives me a -3x minus 3y, because that applies to all items, equals a -30. Don't forget to put that -3 on all items on both sides of the equal signs. Down below, everything's the same. 3x plus 2y is equal to 15. And all I'm going to do, like usual, is now add them together. And because I put in the work beforehand, it's a nice easy addition. 3x and -3x cancel. 2y minus 3y gives me a -y. And then over here, a negative 30 plus 15 is a negative 15. I'm going to divide by a negative on both sides. That gives me that y is equal to positive 15. And like always, I'm going to take that 15 and plug it into one of the originals. The first one looks pretty easy. So in the first one, I have an x, I have a plus, and then this y is going to become a positive 15 is equal to 10. Just replacing this y with this y value. This gives me that x is equal to, if I minus 15 to both sides, a negative 5. And so I have my solution to this problem, which is the coordinate negative 5 for x, comma 15 for y. And that's my solution. All right, let's check out a tough one. So let's see what's going on here. We have 2x plus 3y equaling 12, 5x plus 4y equaling 10. So at least the x's and y's are lined up, but these are both positive, so I'll have to bring a negative in somewhere. And what's really annoying is I can't just multiply one of these equations by anything. So for example, this 2x, in order to get it lined up with this 5x, I can't multiply by any whole number. 2 times 2 is 4, 2 times 3 is 6. Neither of those would line up and make this 5x go away. Similarly, for 3 and 4, I can't just multiply 3 by 2 and have it line up because 4 doesn't match up with any multiple of 3. So what are we going to do? We're going to look for, ideally, the least common multiple of these. Now, you don't have to have memorized any fancy formula or method of solving for that. Just kind of check and test some numbers. And if you're not sure, you can always just multiply them together. And it won't be the most efficient answer, but it'll still work out. So let's see what that looks like. I'm going to think, I'd like these to work really well together. It'd be great if they were both a 12 because 3 times 4 is 12. So I'm going to do exactly that. On the top one, I'm going to multiply it by 4 because 3 times 4 would give me that 12 I need. And on the bottom one, I'm going to multiply it by a negative 3. Why a negative? Well, because they're both positive and I have to have something go away. And then why a 3? Well, it's because 3 times 4 gives me the same 12. So I'm just multiplying by each other. This has a 3, I need a 3. This has a 4, I need a 4. I could have done the same thing with the x's of choosing a 5 and a 2. So I do a 5 up here and a 2 down here. But I just went with the y's, and it's up to you which one's more convenient. So let's follow through and see what happens. The result of this is that we get 8x plus 12y is equal to, and don't forget to multiply on the other side of the equal sign as well, 48. For the second equation, I get a negative 15x because of that negative 3 minus a 12y is equal to a negative 30. Now things are lined up nicely for the y's to go away. So I simply add them together. And that's what I want to have happen on every problem here. So 8x minus 15x is going to give me a negative 7x. The y's are going to cancel. And on the right side, I'm going to have a positive 18. Now this ends up being an ugly number, but that's okay. X is equal to negative 18 over 7. Can't simplify it, so I'm just going to leave it like that, and that's fine. That will make this difficult to solve for the next variable, the y, but that's okay. We'll just go slowly and step by step. So I'm going to take this value for x, I'm going to plug it in to one of the beginning equations. I'm going to try and stick to the original equations. I don't like to go for the equations we've messed with too much. So I'm going to go into the first equation. Why not? So I put a 2, parentheses, and negative 18 over 7 plus 3y is equal to 12. Now, this is going to give me a negative 36 over 7, just 2 times 18, plus 3y equals 12. Now, you may need to review a little bit of your fractions for this to make much sense, but all I'm going to do is add this number over. I have a negative number. To get rid of it, I'm going to add it over. This gives me that 3y is equal to 12 plus 36 over 7. Now, in order to add fractions together, I need a common denominator. So I'm going to multiply this 12 by 7 over 7 in order to match this 7 denominator. This gives me 3y is equal to 12 times 7, which is 84 over 7, plus 36 over 7. Now, because there's a common denominator, I can clearly add them together. I get 3y is equal to 120 from the 84 plus the 36. Now I divide by 3 on both sides. I get that y is equal to 40. That turned out fairly nice. And so my final answer is going to be the coordinate pair of an x value, negative 18 over 7, and a y value of 40. And that's my final solution. Now, that was tough because I had to do a multiplication on each equation. I had to put a negative on there, and I ended up with fractions. But I hope you see that it's very manageable, and it's the same system every single time. Let's check out some curveballs, some weird ways they can mess with these equations to make it seem more difficult. Here we have 1/2 x plus y equaling 5, and 2y plus x equaling 12. What did the teacher do to make this difficult here? They threw in a fraction, which scares students, intimidates them, and makes you panic. However, if you don't like fractions in these systems of equations, we can actually just get rid of them. So in order to get rid of this 1/2, I'm going to multiply everything by a 2. Just times it by 2. And it's going to go away. Now again, this isn't really part of solving the system. This is just me making it look nicer so it's easier for me to mess with. This gives me 2 times 1/2 being 1, a singular x plus 2 times y is equal to 10. Don't forget to multiply the 2 on that 5 as well on the other side of the equal sign. For the second equation, we get that 2y plus x is equal to 12. We didn't really change it. And now it actually worked out really nicely. The 2y and 2y look like they're going to cancel. So I'm going to do some rearranging, and that's going to give me that x plus 2y is equal to 10, and x plus 2y is equal to 12. Now something very strange is going to happen. I have an x plus 2y and an x plus 2y in both equations. Normally, what I'd like to do is get one to be a negative, and so we'll see what happens when I do that. I'll get a negative on everything on the bottom, because it looks like it's lined up for the y's at least. That's going to give me that x plus 2y equals 10, and negative x minus 2y equals negative 12. But when we go to add these together, what we get is the left side cancels everything. So what do I write? Do I just add up the right side, write a negative 2, and that's my solution? No, because then I have no x to set equal to, no y to set equal to. These don't just disappear. They turn into a 0 equaling negative 2. And that is not true. 0 does not equal a negative 2. So what's going on here? What's going on here is that we have two equations with no solution. No solution, right? And that's because if these were to be lines, for example, they are parallel lines that will never cross. So these two lines never cross. There is no solution between them. And we can tell because we get a ridiculous equality, 0 equaling negative 2. And anytime you get a ridiculous equality that is simply never true, you can say there's no solution to your system of equations. Let's check out one more. All right, so here we have x minus 2y equaling 4, and 2x minus 4y equaling 8. Now in order to solve this, like normal, we're going to try and line it up, x on x, y on y, which is good. I do see there is no negative mismatch, so I can't just add them to get rid of it. And I also see that they're not lined up. So I would have to multiply something maybe on the top equation to get the coefficients, the numbers next to the variables, to match. So I think on the top, I'm going to line up the x's, and that's going to mean I'm going to need a times a negative 2 on the top. A negative because they need to mismatch signs, so I can add them and they go away. And a 2 so that it becomes the same as the 2x. This is going to give me a negative 2x plus a 4y equaling a negative 8. The second equation is going to be a positive 2x minus 4y equaling 8, because again, I didn't change them. When I add these together, I get a 0x, negative 2x, and 2x give me a 0x, but I also get a 0y. And so I'm going to put down here a 0, like we learned from the last one. It doesn't just go away, it turns into 0. But interestingly, on the right side, I get a negative 8 plus 8, which is also 0. So unlike the last time where we had an equation that made no sense, and so we had said no solution, we can't say no solution here. It is not the case that there's no solution. It is the case that there are infinite solutions, because 0 equaling 0 is always true. It doesn't matter what x or y is, 0 will still be equal to 0. So I would write infinite solutions as my answer for this. And that will occur anytime you have an equality that is always true regardless of variable. If I got a 5 equaling 5, 7 equaling 7, smiley face equaling smiley face. Any of these situations would give me infinite solutions because they're always true without any regard to the variables. Visually, what that means is you have a single line, and then the next line you tried to graph was right on top of it. And so they're the exact same thing. They're always going to match up. They're always going to line up. They're exactly the same. And this would be your final answer. So as a recap of everything we've talked about, systems of equations are when you have two equations set up next to each other, and you want to solve for the variables that make them both true at the same time. One method of solving them is going to be elimination. It's where you get rid of a variable. Once you get rid of a variable, you're going to then be able to solve for the other variable. And once you have that other variable, you can use it to once again solve for the original variable. This will leave you with two parts of your solution, an x value and a y value. So you would write your solution as parentheses x comma y. Some curveballs they can throw at you in this process include mismatched x and y, which forces you to rearrange your x and y values, a mismatch of signing, which requires you to throw a negative on one of the equation. They could throw in some fractions at you to scare you, in which case you can just multiply by the denominator to get rid of them. And lastly, you can end up with either an infinite solution or a no solution. And this is going to come from either getting an equation that is always true, 3 equaling 3 for an infinite solution, or an equation that is never true, 3 equaling -5 for a no solution. And with that, you're fully prepared to tackle any elimination problem.